For Lab 1, we were required to observe and record an object moving in the same direction at the same speed. We then had to analyze the video and compare it to a computer model using the principles from Newton's second law, all of which I will go into more detail with later. Newton's second law is relatively similar to the momentum principle. Both of these equations allow us to predict the future position of a system a short period of time into the future with a little manipulation. All we need to know is how fast the system is moving and in what direction, as well as the mass and net force. For my video, I recorded a lacrosse ball rolling across a set of brick stairs. I later trimmed it down to a section of the video I felt best showed the system traveling in the same direction at the same speed. Once I put this video in Tracker, I was able to extract the initial position and initial velocity as well as some other important information needed for my code. I was also able to find the mass of the system in SI units. All of this information was needed to complete the Newton's law aspect of my program. Here you can see my code, which includes a lot of information from the earlier slide. This code produced a graphic showing the motion of my ball as well as a graph showing time versus position data. It also prints a series of coordinates which I was able to put into Google Sheets to create a graph comparing the model and experiment data. I used the datasets from the code, as well as the datasets extracted from Tracker in my experimental video to produce this chart. The experimental points are in blue and the model is graphed in red. We can tell the difference because the model is constant due to Newton's second law, but the experiment is not due to outside forces. These forces in my case include the fact that my surface was not completely flat. You can also see the ball fall off the steps toward the camera at the very end of the video. Though this was not included in my analysis, we can assume that the ball was traveling slightly in the positive y direction throughout the entire process of the ball rolling. This explains why my model overpredicted more toward the end of the clip. Finally, we need to address some questions. Firstly, what would happen if we were to flip the axes? In my case, if I flipped my axes, my graph would still be traveling right as time increases. However, instead of traveling in a positive direction, it would travel in the negative direction. Essentially, my graph would simply flip over the x-axis. Secondly, is it possible to say how many pushes or pulls are added together to give a zero net force? We can always speculate on the number of pushes and pulls on our system. In my case, this could include friction from the bricks, gravity, wind, and many other forces all the way down to an ant who happened to be in the path of my lacrosse ball. However, we can never truly know how many pushes and pulls are on a system in the natural world as mine was. The system would have to be in a completely controlled environment in order to know every force acting. Though in the natural world we may never know exactly how many pushes or pulls act on a system, we can always use Newton's law to help us predict what that system is going to do.